Okay. Okay, is the screen visible? Okay, we have seen this task interaction graph for a particular matrix, sparse matrix vector, basically multiplication problem. This was a sparse matrix that we had seen in the last lecture. Sparse matrix means what? It is not having lot of non-zero elements. More number of elements are zero in this matrix, then it is called as a sparse matrix. So sparse matrix into a vector B, it is a column vector. Okay, column matrix. So it had a task interaction graph shown in figure B. See, each node in the task interaction graph is a task. You can easily see row wise there have been tasks that have been put into the basically the for the matrix. So task 0 is represented by task 0, 1 is represented by task 1 and so on. Okay. So what happens is that the vector B needs to be communicated between the tasks. Okay. So 0 task is giving the vector B value to task 1, to task 4 and task 8. So you can easily see 0 task is connected to 1, 4 and 8. Similarly, task 1 is giving it to task 1, task 0 rather, then it is giving it to task 5 and task 6. So 1 is giving to 0, 5 and basically uh, 6. Okay, so this way the you are having the basically links edges in the task interaction graph, because B vector is being communicated. This is the communication that is happening between the tasks for executing the sparse matrix vector multiplication problem. So the tasks are communicating the values of the vector B between them. Okay, so that is shown by the edges in the task interaction graph. Getting this concept, the tasks are communicating the vector B values between the tasks. So they are shown by edges between in the task interaction graph connected by tasks which are connected by edges showing the interaction, that is communicating the value of vector B to each other. Getting the concept of this particular task interaction graph, because task interaction graph shows the interaction between the tasks, communication between the tasks. So you can easily see that task 0 is giving it to 1, task 1, task 4 and task 8. So task 0 is connected by edge to task 1, task 4 and task 8 and so on, because the vector values of the B vector, the zeroth B0 value is communicated between the 0 column of all the tasks. One basically value is communicated between the first column of all the tasks. Okay, getting this how the task interaction graph has been drawn. It is a little advanced concept, but understand it logically so that you get it properly. We don't need to go too much into the example. It is just a sample task interaction graph, because we have studied about it. I have just shown you a sample task interaction graph, how basically task. So it is the age between the task is showing that data exchange is happening between the tasks, communication is happening between the tasks. Getting this? Yes, everybody is clear with the task interaction graph. Okay. Then the next concept is task interaction graphs, granularity and communication. So in general, if the granularity of a decomposition is finer, the associated overhead as a ratio of useful work associated with a task increases. So what happens is that when the decomposition is finer, when you say decomposition is finer, that means what? Yes, what do you mean by decomposition is finer? Yes, what do you mean by decomposition is finer? We are saying granularity is finer. Is the meaning that decomposition is finer. What do you mean by that? Yes, recall that we had seen I think one or two lectures back. When I say that decomposition is finer, what do you mean by that? Yes, that's correct. More number of tasks the problem is decomposed into. There will be more number of tasks when the decomposition is finer. And when it is coarse, decomposition is coarse, it means less number of tasks. Okay. So when you have more number of tasks in which the particular problem is divided into, the overhead of communication also increases. Okay. So what happens is that when you decompose a particular problem into more number of tasks, basically uh, the overhead of communication also increases. Okay. So that's why they are saying that the associated overhead as a ratio of useful work associated with a task increases. So more overhead of communication becomes because of more number of tasks. Okay. Example, consider the sparse matrix vector product example from previous foil. Assume that each node takes unit time to process and each interaction edge causes an overhead of a unit time. So unit time for the task to execute and each edge is taking unit time. That is what assumptions they have taken for that particular task interaction graph. Viewing node 0 as an independent task involves a useful computation of one time unit and overhead communication of three time units. So if you look at the task interaction graph, 0 is taking one time unit to execute its work, and since it is having three edges, the overhead is of 3 units. Okay, so that is what they have analyzed for the task 0. Its useful time is 1 unit and overhead is 3 units. Okay, that means you can easily see that the useful computation is very much less as compared to the overheads. More overhead time is being utilized because of the more number of tasks that have been put in the particular task interaction graph for the problem. Okay. Now if we consider node 0, 4, 5 as one task, so we are not making it finer, we are making it coarse. In the earlier point, we have said a finer task decomposition. Now, if we reduce, we take multiple tasks as one unit. 0, 4 and task as one task we are taking. Node 0, 4 and 5 as one task. Then what happens is that the useful computation becomes 3 time units and communication overhead becomes 4 time units, 4 edges. That means 0, 4, 5 is a one task we are taking, one node. So there are 4 edges going out from this one task. Okay. So what it means that useful time is 3 units and overhead is 4 units. So clearly the overhead has reduced when you reduce the number of tasks into which a problem is getting divided into. Getting this? So when you make it finer, the overhead also increases. When you decompose finer, the overhead increases, and when you decompose coarse, the overhead reduces of communication between the tasks. Getting this? When you decompose finer, the communication overhead increases, and you when don't we reduce the number of tasks or the problem, the communication overhead reduces. Are you getting this point? So all this has to be considered when deciding the solution for the problem in parallel platform. Okay? Yes, everyone, are you getting this point? Okay. Now processes and mapping. In general, the number of tasks in a decomposition exceeds the number of processing elements available. So normally what happens is that the number of tasks into which the problem is decomposed is normally more than the number of processors or processing elements which are available in the parallel platform. Okay, so there are more number of tasks for a problem as compared to number of processors in the parallel platform or processing elements in the parallel platform. For this reason, a parallel algorithm must also provide a mapping of tasks to processes. Okay, so task to processes mapping is done in parallel platforms. We refer to the mapping as being from tasks to processes as opposed to processors. So what is done is that tasks are mapped to processes, not directly to processors. This is because typically programming APIs, as we shall see, do not allow easy binding of tasks to physical processors. So it is difficult in programming to directly bound a task to a physical processor. So what is done is that rather we aggregate tasks into processes and rely on the system to map these processes to physical processors. So what is done is that tasks are collected together into a process, and those processes are mapped to the processors. Okay, instead of mapping the tasks directly to the processor, the tasks are collected together in processes. So multiple tasks in one process, and those processes are then mapped to the processors by the platform. Okay, the platform of that particular parallel computer will map the processes to the processors. We use processes not in unique sense of a process, rather simply as a collection of tasks and associated data. So don't confuse this process with the Unix process, programming execution and all that. Here what is happening is that tasks and the associated data are basically put in a process. This is the process in parallel computing. Okay, don't call process as a program in execution. This is the process that is mapped to the processor. It is a collection of tasks and data associated with the task. Getting this? That means what? Tasks are not directly mapped to the processors. Tasks are mapped to the processes, multiple tasks in one process, and that process is then mapped to the processor by the system of the parallel computing platform. Okay? Getting this? See, get used to some concepts of HPC, because I told you this is not very simple subject. We are studying not only the programming, but we are also studying the OS, the hardware, everything. All the concepts have been put in this subject. We are not just going to study programming of HPC. We are going to study how the OS has got designed, some part of it, how the particular hardware has got designed. So all these concepts have been put in this one subject. So we are discussing the whole parallel computing platform as such. Obviously, programming part is also there. How the OS has got designed is also there. How is the hardware got designed is also there in this subject. Okay, so you have to little bit think on that and accordingly understand the concepts. Okay, so they have gone into a lot of depth in this particular subject while giving this syllabus. Okay, okay. Then speaking about processes and mapping, appropriate mapping of task to process says is critical to the parallel performance of an algorithm. So the task should be mapped to the processes properly so that the performance of the algorithm is good on the parallel platform. Okay. Mapping are determined by both the task dependency and task interaction graphs. So mapping is decided from the task dependency graph and task interaction graph of that particular problem. Task dependency graph can be used to ensure that work is equally spread across all processes in at any time. Minimum idling and optimal load balance. So task dependency graph is used to ensure that work gets equally spread across all processes. What does task dependency graph give? We already discussed. What does the task dependency graph give? It gives the control dependency. You answered that few minutes back, isn't it? Task dependency graph gives the control dependency. So what happens is that it ensures the control dependency is used so that the work gets equally spread across all processes at any point. So the control dependency means what? First, before node has to be executed, then the next node can be executed. That is given in the task dependency graph. So the nodes that are at the same level can be executed parallelly. That is what it indicates. They are independent of each other. So nodes at the same level are independent of each other and they can be given to parallel processors. Okay, processes can be allocated to such processors. So task dependency graph will see to it that how all the processes are properly executed. Okay, and task interaction graphs can be used to make sure that processes need minimum interaction with other processes rather. So task interaction graph, what it gives? Data dependency, communication between the tasks. So wherever there is more communication, those tasks are put in one process so that the communication overhead is reduced. So task interaction graph decides on the communication reduction part and task dependency graph decides on which processes can be parallelly executed. So dependency in the processes is found out from task dependency graph to identify which processes can and tasks can be parallelly executed, and task interaction graph decides where is the communication more between tasks so that those tasks can be put in one process. Okay, getting this? See, we are going into how the hardware and the OS actually work in such particular platforms. So you'll have to be little bit active in thinking and learning this particular subject. This is not at the programming level. We are discussing these points at the OS and hardware level of that particular parallel platform. So everybody got this concept? That task dependency graph will find out which processes can parallelly execute. Okay? And task interaction graph will find out where communication happens between tasks and processes so that they can be grouped together so that communication overhead can reduce. Getting this? See, everybody got the PPTs or that I shared on the Google Classroom of the Unit 1. I've shared the PPTs of Unit 1 because we have completed that on Google Classroom. Just go through it. And I told you there are some extra slides also beyond syllabus. So follow the syllabus while reading the particular PPT. They are in brief, obviously, but I've kept it for content beyond syllabus for you also. So I didn't remove those PPTs that were extra in the particular PPTs. Okay. Everybody saw that in the Google Classroom? Okay. Are you finding it useful, those PPTs? See, it is in brief. If you directly go to the reference book or local books, you will find you will be more confused with the concept if you don't read it before the PPTs I'm discussing with you. Because this subject is lot of depth basically. They have given it in lot of depth actually. It is simple, but in depth it has been given. So PPTs will be very helpful for you to short summarize the concepts and understand the concept, and then you can refer the reference book or maybe whatever local publications you are using. Okay, so in brief you can understand the topic in the PPTs. Have you seen the reference book, everyone? Yes, anyone has seen the reference book? If you're not seen, maybe I'll share it with you on the mail or the Google Classroom. So if you look at the reference book, you'll understand what I am saying. In the reference book, there is a lot of data given on the every topic. So if you directly go to read the reference book, you'll get confused a little bit. You can do that, even if that's a good habit actually. But first, if you revise from the PPTs and then read the reference book, you will understand it more better. Okay, I'll share the reference book also with you. Okay, in 1 or 2 days, so that you start the studies using the reference book also. Have you got the local books? Are they available now? Local books are also not available. Okay, no problem. I'll be sharing you with the reference book, and I'll be sharing the PPTs as soon as we complete every unit. So after every unit, I'll be sharing with you the PPTs of the that unit. Okay. Okay. So speaking about again the processes and mapping, an appropriate mapping must minimize parallel execution time by mapping independent tasks to different processes. So independent tasks should be given to different processes so that they execute in parallel. So normally the tasks at the same level in the task dependency graph are independent. Okay. Assigning tasks on critical path to processes as soon as they become available. You know the critical path. The longest path in the task dependency graph is the critical path. Okay. So the critical path should be basically alloc should be allocated to processes as soon as they are available. Okay. Minimizing interaction between processes by mapping tasks with dense interactions to the same process. As I told you, those tasks which are having lot of interaction in them should be given to the same process so the communication overhead is less. Okay. So that is also another important thing, that communication overhead should reduce in the task from the task interaction graph. We know that. Okay. These criteria often conflict with each other. For example, a decomposition into one task or no decomposition at all minimizes interaction but does not result in speed up at all. So if you don't decompose the problem, you make only one task for the entire problem, then obviously the communication will reduce because there is only one task. But then there is no parallelism. Nothing will execute parallelly. So you have to balance the communication overhead with the performance benefit available by having more tasks. Okay. So you cannot have lot of tasks also and too few tasks also. You have to balance between that. Balance between not having too many tasks and not having too few tasks. Between that you have to balance and get the best performance from the parallel platform for a given problem. Getting this? Yes, everybody is understanding the concepts. Okay. Any difficulty so far? Yes, anybody is having any difficulty specific to any topic in the second unit? See, you must be wondering how it is getting used, basically all this concept. So as I told you, it is not getting only used at the application level. All these concepts that we are discussing are also getting used at the OS level and the hardware level. I'm again repeating that point so that you understand where it is getting fit into. The ones who are designing the operating system for the parallel computer will need all these concepts. The people who are designing the hardware for the parallel computers will need all these concepts. It is not necessary because you saw in the practical, we use the program of OpenMP. So it was at the application level. So there the algorithms and programs will come into picture. But to execute those programs, there has to be some work done on the OS level and the hardware level. So there all these concepts will be getting useful while designing those particular parts of the parallel computer. Okay? And obviously that is also not the only sufficient thing. Somebody has to write the application programs also. So that also has been given in this subject. Okay? In the particularly fifth and sixth unit. Okay? So speaking about processes and mapping example, so this is the database query decomposition basically that had been the dependency graph. Okay. This is the task dependency graph of the database query. We had seen two methods of the database query which we were executing and then the task dependency graph for that we had seen. Okay. So every node is a task. Okay. So no two nodes in a level are dependent on each other. So if you look at here, P1, P0, P2, P3 are the task 1, task 2, task 3, task 4 are basically independent of each other. So they can be given to different processes for execution. Okay? Whereas task 3 and task 6 are dependent on each other. Okay, so at the same level the tasks are independent of each other, but at different levels the tasks are dependent on each other. So when they are dependent, they should be given to the same process, whereas the tasks which are independent should be given to different processes. That is what they have shown using an example. Tasks have been given and the processes allocated to that task has been shown in the particular diagram. So this is an example of tasks and processes mapping. Okay, these tasks have been mapped to processes. Task 4 has been mapped to process 3, task 3 has been mapped to process 2, task 2 has been mapped to process 1, and task 1 has been mapped to process 0. So since they are at the same level, all these tasks, they have been mapped to different processes. Whereas when they are at different levels, they have been mapped to the same process, because till task 1 executes, task 5 cannot execute. Till task 5 completes execution, task 7 cannot execute. Okay? Getting this? So how from the task dependency graph, if the processes are at the same level, they are basically allocated to processes are close to processors. Processes finally get mapped to the processors. So you can say indirectly the tasks are getting mapped to the processors basically. Okay, how the tasks are getting mapped to the processors through the processes, that is what is being done in this particular diagram. They have modified the task dependency graph to map it to the processes also. Getting this? How the task is getting mapped to a process, that has been shown for this example. We have seen the query example, isn't it? Database query example. If you recall, database query example. So this was the example that we had seen in one or two lectures back. So that is a task dependency graph for this example, database query example. So for that, this is the data dependency graph with tasks. And that has been, these tasks have been mapped to a process that they have shown. Getting this? I hope you are understanding the concepts. I know they are in deep basically, but I am showing you examples also for every concept as much as I can basically. Yes, understand the concept. These were the basics of the second unit that we are discussing in last two lectures. Then we'll start with the actual some methods and techniques that we are going to study for parallel computing. Okay? These were some of the important concepts that are there in the second unit. Okay? Yes, getting this? Any difficulty? And do the study of HPC regularly. It is not a subject that you can study in the last and get over it. It is in depth basically. You can easily see so many concepts. Almost in every lecture we are talking about a new concept. So a lot of concepts are there in this subject. Okay. Resources are available. PPTs are available. Reference book is available. You have local books, but you will have to study it regularly. Keep a habit of studying this subject regularly. Don't take it lightly basically. It is not that simple subject, so take it lightly basically. It is a good subject, easy subject, but don't take it lightly. Okay, then it will be benefit to you if you study regular. Okay. Okay, give me 2 minutes. I'll just take your attendance.